what this class is about. We show you how to do things, and then just when you thought you understood it, we give you a challenge, and hopefully you still understand it. Right, so I want to gather round because I'm going to show you what you're going to be doing for the next 20 minutes. And it's really just building on what you've learned so far, okay? Right, so anybody want to photograph this, do so now. Otherwise it's going to be forever gone. Okay? Bye-bye. So, it's alright, the next one's pretty similar anyway. Right, I told you about the potential divider equation, right? What is the potential divider equation? Somebody tell me? So, it relates to this. Again, this isn't an integral part of what we're doing, this is just for interest while you're using the simulator. Somebody give me the equation for the potential divider. That's right, so actually it's V out equals V in R2 on R1 plus R2. In other words, it's going to give us the voltage out as a function of the voltage in. Now those of you who have done some electronics before, that's also called a transfer function. So we've got the transfer from the input to the output based on a simple equation. Okay, so that's resistors. Of course, capacitors and inductors aren't resistors. They have impedance, but they're not resistors. And their impedance, which is the AC equivalent of resistance, depends on what the frequency is. Does anyone know the equation for the impedance of a capacitor?
1 over 2 WC, something like that.
FC.
Good. Good. Now where we go on the omegas and so on, yes, it's a complex impedance, and yes, we could do complex analysis and resolve the vectors, magnitude and phase and everything. But that's just quite a convenient way to represent, so we've got XC, so that's the impedance of the capacitor, because notice that the impedance is dependent on the frequency. The capacitor isn't going to change, 2 is not going to change, pi hasn't changed for a few years that I'm aware of, so F is probably going to be the only variable which is in there. Okay, so what does that tell you? It tells you that the impedance, as the frequency increases, what happens to the impedance? Okay. And we have a corresponding one for the impedance of an inductor, because an inductor also behaves in a similar way in that its impedance changes according to frequency. What's the equation for that? I know you know this one as well, so tell me.
Isn't it 2p 2p that's it?
2 pi f. Oh, sorry, I'll bring that down a bit. I get so used to writing things over 1 now, just because I do some funny maths. But the so XL is equal to 2 pi FL. Okay. So you saw that before we put the capacitor here, and it had a high pass operation. In other words, a low frequency, do it this way around. So at low frequency, you've all seen this graph lots of times now. At low frequency we had low amplitude, so this is the amplitude, this is the frequency. At low frequency we had low amplitude, and at high frequency we had high amplitude. So what we're going to do now is just a very, very simple swap. I'm going to put the capacitor here. Now if I put the capacitor there, with things like this, the easiest way to perceive any circuit, and this even goes into some very advanced electronics, when you see a circuit, there's certain things that you can tell about it straight away. What's the one thing I can tell about this circuit straight away? Well, look at the impedance. You've already told me that as frequency increases, the impedance goes down. Yeah? So what that means is if I magically fire high frequency into here, what's going to happen? What's going to...
Low impedance.
Forget the impedance. What's going to happen if I feed high frequency into here? What's going to happen to the waveform? It's just going to... Is this going to be in conduction or is this going to be in high resistance or high impedance rather? Don't be frightened. You get it the wrong way round. There's only one other choice. Is this going to conduct at high frequency or not? Show of hands for yes. Show of hands for no. The yeses have it, unfortunately. So at high frequency, that capacitor is going to appear to be pretty much like this. It's going to appear to be a short circuit down to ground. So, if I have coming in here 10 volts, say for example, because that's what you were using, all of it's going to get dropped across the resistor there because this point here is 0 volts, and so is that, if it's short circuit. Okay? So at high frequency, my output's going to be 0. Well, that's actually the other way around to what we had before, isn't it? So, what I know, just from that very simple observation here, I know that a capacitor conducts rather well at high frequency. So at high frequency, if I think about it, if this suddenly becomes short circuit because there's high frequency, this is 0 volts here, so this must be 0 volts here, which must mean this wave is dropped across the resistor here. What I end up with, so this is frequency going up. At high frequency, I have a low amplitude. Okay. What happens if I feed a low frequency into that capacitor? It shouldn't be too hard to produce now. So what do capacitors do to low frequency? Do they let it through or do they block it? Okay, hands in the air for letting it through. Hands in the air for blocking it. Okay, the blocking it's have it. So at low frequency, because this isn't changing, this capacitor will block. Won't let that signal through. Okay? So by blocking it, well actually, the capacitor looks like it anyway, but by blocking it, that wire is effectively not there. So if that wire's not there, well if I've got 10 volts here, I must have 10 volts here. So in other words, at low frequency I have another point here which shows that the amplitude is at a maximum. Now you can plot your graph in the same way as you did before, but effectively what you have is a waveform that looks like that. So this is high pass, that's what we had before, and this is low pass. And just derived from first principles. All we're doing is we're saying that we know the capacitive reactance from this equation here. So from that we can deduce that at high frequency this is a short circuit here, and at low frequency it's an open circuit. So we can look at any circuit that we want and we can say, okay, what's the input capacitance? If we know what the input capacitance is, we can work out what's going to happen to the signal that we feed in there. It could be a very complicated circuit, but as long as we know the input capacitance and the input inductance, we can predict what's going to happen to it. That's marvellous. Because that's for a whole circuit. That might be for an amplifier, that might be for a box of electronics and you've got no idea what's in there. As long as you know what that is, you can start to predict how much conduction it's going to have. Okay, enough of the theory, and as I've said to you before, this is here for understanding. That's all it is. Now, I'll just do one step further. So if I assume that this is R1 and this is R2, if I feed that into this equation, what I get is the same as I had before. So I get V out is equal to V in, but now R2 is 1 upon 2 pi FC divided by R1 plus 1 upon 2 pi FC, and then I've got an equation which defines that in terms of capacitance. You can tidy that up because you can multiply top and bottom by 2 pi FC, and what you get is a 1 on the top. So we've got V in, we've got 1 on the top, 2 pi R1 C1 plus 1. So there's an expression which gives you the output as a function of the input for the capacitor. But you don't need to know that. But there's some lovely little derivations associated with this where first principle mathematics actually predict what this output's going to be. How do you think the simulator does it? Does it in the same way. So it works out, well, it does it through mesh analysis, but it works out what the equation is, and it feeds that through and it plots the graphs for you and so on. Okay, so that's just more for interest than anything else. What I want you to do is I want you to design me, and I don't want you to plot it by hand this time, I want you to do it in the automated way like we did on the board. I want you to design me a low pass filter, one of these, and I want that low pass filter to have a cut-off frequency of 6.8 kilohertz. Okay, so that's your challenge for the next 10-15 minutes.